In the last video, I had designed SOI MOSFET and the dimension of the proposed structures are doping concentration of source and drain is 10 raised to power 20, doping concentration of the substrate is 10 raised to power 18, doping concentration of the channel is 10 raised to power 18, thickness of the oxide used 3 nanometer, this one, this one. Total length of the MOSFET is 500 nanometer, length of the channel 100 nanometer, width of the bulk MOS is 100 nanometer, width of the oxide layer, this one, is 30 nanometer. Let's go to the code. This is my code. If you want to understand the writing of the code in Silvaco, please go to my last video. The name of the video is Silvaco TCAD tutorial for design of SOI MOSFET. You can also copy the same code and run on the Silvaco to find out the same result. This is my code. Go Atlas. These are the meshing for x-axis and the y-axis. Next is the region with the material, region 1 to 5 with different material, air, SiO2, silicon, SiO2 and silicon. Next one is the electrode name, gate, source and drain with the positional parameter. Next one is the doping concentration for source, drain and bulk with their positional parameter. Next one is the interface charges at the SiO2 interface. Next one is the contact for gate, source and drain. Next one is the model. Next, this code is used to find out the various parameter in the structure file. Next one, we are using the two method Newton and trap. Next, we are using the source statement to define voltage at different terminal. Next one is the solve AC frequency. This line is used for the store the capacitance in the log file. Next, we have to save these structure file and the log file. We can observe these file only in the Tony plot. Go for the PPT. This is my proposed structure. This is my final result file. That is the .str structure file. Next one is the .log logarithmic file. Log file contains two curves, linear curve as well as logarithmic curve. Left side of the y-axis is in logarithmic form and the right side of the y-axis is in linear scale. Next result is the capacitance result. In MOSFET, the gate capacitance is very high as compared to gate drain capacitance. You can observe in the figure. In this video, we will talk about the outcomes coming from the log file such as drain current, capacitance, subthreshold slope, threshold voltage. The output coming from the structure file such as energy band diagram, electron hole concentration, electron density, potential, electric field, etc. We will discuss these parameters related to the .str file in my next presentation, which is based upon design and characterization of double gate MOSFET using Silvaco TCAD tool. So let's start. To study the impact of process variation on the characterization of SOI based MOSFET, in which I have considered different factors such as doping concentration, source drain channel doping, work function of metal, gate length, oxide thickness variation, drain to source voltage. To understand these parameters, you first know what is threshold voltage. Threshold voltage is defined as the minimum gate to source voltage at which device enter into the on state. For NMOS, VT is positive. For PMOS, VT is negative. For better performance of the device, threshold voltage must be as small as possible. It is defined as VT. In this presentation, we will talk about how these parameters, doping concentration, gate work function, gate length, oxide thickness, drain to source voltage affect the drain current. By changing the source doping, what would be the change in the drain current by changing the different work function, different type of metal at the gate, the very effects on the drain current, the variation in the gate length effects on the drain current. So we will discuss these points one by one. The first one is the doping concentration of source and drain. First one is the doping concentration of source. This is the graph showing the impact of variation in doping concentration on drain current, in which I have varied the source doping from 10 raised to power 16 to 10 raised to power 23. The doping concentration is directly proportional to the threshold voltage and on current. Below this, you can see the equation. This one. VTH is directly proportional to the Na. Na is the source concentration. As we increase the source doping, the value of the threshold voltage is increases and the on current also increases. You can observe in the figure. The on current is increasing. If you are increasing the source doping, then the threshold voltage corresponding to the 10 raised to power minus 7 current is also increases. Next one is the doping concentration of drain. This graph show below the variation in drain doping. We varied the drain doping from 10 raised to power 18 to 10 raised to power 23 and study its effect on the IDVGS curve. As we increase the doping concentration of the drain, then threshold voltage will decrease and the on current will increase. You can see in the figure. The gate voltage corresponding to the required current for the VT 10 raised to power minus 7 to corresponding the gate voltage. You can observe the red line and this one is the yellow line. The gate voltage corresponding to the drain current 10 raised to power minus 7. For yellow curve, which having doping 10 raised to power 23, and for the red one, it's 10 raised to power 18. The gate voltage, or we can say that the threshold voltage for device having doping is 10 raised to power 18 is high. This means if you are increasing the drain doping, the threshold voltage will decrease. Next one is the gate work function. This is the graph showing the impact of variation of gate metal work function on drain current. In this, gate metal work function is varied from 4.1 electron volt to 4.6 electron volt. The threshold voltage is directly related to the difference between the work function of metal and substrate. So if we increase the work function of metal electrode more than the substrate work function, then the threshold voltage will increase and the on current will slightly decrease as shown in the figure. As the work function decreases, I of current increases. Or we can say that if your work function increases from 4.1 to 4.6 electron volt, then off current decreases, which is desirable. Actually, the curve is shifted right side as you increase the work function of gate metal. This graph shows the impact of variation in oxide thickness on drain current. The variation of oxide thickness from 1 nanometer to 6 nanometer is shown in the figure. The outcomes ID is directly proportional to oxide capacitance COX. COX is defined as the ratio of epsilon OX divided by TUX. This equation shows that the drain current is directly proportional to the dielectric constant of oxide and inversely proportional to the thickness of gate oxide material. This means if you are increasing the oxide thickness, it will reduce drain current value. One more thing, it is important to note that the threshold voltage is directly proportional to the oxide thickness. So if we keep on decreasing the oxide thickness from 6 nanometer to 1 nanometer, then threshold voltage will also decrease, which is desirable. But along with this, the leakage current might also increases. You have to must take care of that because some of the electron will cross the thin oxide easily and will be collected at the gate terminal. And this is how the leakage current will increase. So we consider equivalent oxide thickness. An equivalent oxide thickness is a distance usually given in nanometer which indicates how thick silicon oxide film would need to be produced the same effect as high K material being used. Device performance has typically been improved by reducing the thickness of silicon dioxide. But there is a trade-off between the oxide thickness and threshold voltage. So we choose equivalent oxide thickness. EOT is equal to T high K into K SiO2 divided by K high K. T high K is the thickness of high K material. K SiO2 and the K high K are the dielectric constant of SiO2 and the high K material. EOT is decided by ITRS. ITRS is International Technology Roadmap of Semiconductor. 3 nanometer EOT is decided by ITRS for SiO2 material. There are different high K material. For example, Si3NO4, ZnO2, TiO2, HFO2, T2O5, Al2O3, etc. By using the above formula, thickness of different high K can be calculated as for ZnO2 material having dielectric constant 60. EOT by using the above formula is 12.307 nanometer. For TiO2 material having dielectric constant 81, equivalent oxide thickness is 62.3076 nanometer. For HFO2 material having dielectric constant 21.25, equivalent oxide thickness is 16.34 nanometer. For Al2O3 material having dielectric constant 7 to 9, EOT equivalent oxide thickness is 6.15 nanometer. Next one is, this is the graph showing the variation in drain current for various value of drain voltage, as the drain current is directly proportional to the drain voltage. So change in drain voltage directly influence the drain current. On current will increases if we are increasing the drain voltage. So this is all for today. If you like